Hello everyone, welcome back. So in this video, we are going to understand next question we have is very jump game 9, and you are given an integer array nums, and it is from index I can jump to another index j under some, right? What are the following rules are there? Let's understand. Jump to index j where j is greater than I is allowed only if nums at j is nums at I. Another is saying that jump to index j where j is less than I is allowed only if nums at j is greater than I. Okay, so we have to jump to index j where j is greater than I, allowed only if nums at j is less than nums at I. Similarly, we have to jump to j when j is less than I. Okay, and in this case it's reverse. Okay, means it's lesser than and it was greater than, it was greater than, it was lesser than, and it was greater than. Can we say that? So for each index I, we have to find the maximum value in the nums that can be reached by the following any sequence of valid jumps that is starting at I, and we have to return the answer where answer at I is the maximum value reachable starting from the index I. Let's understand the example. Very first, try to understand what the example is saying. That means we have given the nums, we have given, yeah, we have given the nums, right? It's an array, right? And for each index I, we can jump forward to right, we can say, where j is greater than I, right? And nums at j is less than nums at I, right? So you are allowed to jump downward in the value when moving forward, correct? And for index I, when we want to go from index I, we can jump to backward in the left side also, correct? So either you jump forward and backward, but when you jump forward, you can say you can go to the right side when j is greater than I, but when you jump from the backward, right, it become what? From this side, means j should be less than I and should be the left side. Understand? When nums at j is greater than nums at I. So that we have seen here, these two conditions we have seen here. We are allowed to jump, you can say, downward and upward based on the given constraint that we have here. Okay, so we can change the multiple jumps here, 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 like that. We can make the jumps, right? So for each index that we have given in this array I, we can we want the largest number anywhere the array that is reachable. Can we say that? So the problem is we have to find the maximum value you can eventually reach, right? So starting at the every index, what we will do, we'll follow these rules, right? And then we'll try to find the maximum value that we can reach there, right? Starting value, starting index will be anything, right? Every index can be possible, either 0, 1, 2, 3, any is possible. Let's try to understand through the example, then you will understand. Okay, so in this case, let's suppose I'll create an array, and we create, so we can take 2, 1, and index I is 0, 1, and 2. We say that. So very first step, what are the possible jumps are there? Can we say that? The possible jumps. Try to understand. Okay. So from index 0, right? The value is what? Value is 2. Can we say that? So we want to go forward. Okay. When we want to go to forward, the index is what? We have I is equal to 1, right? And from here, because we started from 0 and we want to go forward, what is the index is here? Is 1. So can we say, since 1 is less than 2, since 1 is less than 2, it is allowed. Okay. Then we'll check backward. We have checked the forward. Now we'll check the backward. Okay. So backward, there is no elements are there from the index 0, because we are at here when I equal to here, right? When I equal to here, backward is not there. So we'll say none element is there. Okay, so we can go from where 0 to 1 forward we can go, that is fine. Now try with the index 1. So when we try with the index when I equal to 1, it was when I equal to 0, right? What is the value we have here? Value we have is 1. Here value was 2. Okay, so again we'll check the same thing. We'll go to forward and we'll check the value is what we have here is at here, what you call index, we can say 1 is less than 3, that's fine. We'll check the value here, and the value what we have, no value is there, we can say no smarter value we have the right side. Can we say that? Because this is, we have to take, it was when it was 2 is 1 is less than 2, but this time we have 1, right? And it is we can not like we can say 3 is not less than 1, so there is no elements there, so forward is not possible. Then we'll check the backward, right? When we'll check the backward, we can say we have 2 is greater than 1, and that is true, right? Because we have saw the these two rules. When we go for the backward, when we go to forward, right, we have these rules, right? So when we found this one, so yeah, from here we can go. So we'll say from 1 to 0 we can go. So these are the two possibilities that we have seen till now. Like that we will find for the other indexes. For here, let's suppose at I equal to, we have is 2, and when we go to forward, no elements are there. We'll go to the backward, and both we have is 0 and 1 is there, correct? 0 and 1. At 0 we have 2, at 1 we have is 1, and both are smaller. So here the rules says that we go to backward only if nums at j is greater than nums at I, right? And here 2 and 1 are not 2 and 1 are not greater than 3, so no jumps are there. Understand? That is why we have took this example, and you can see, let me clean it here. We have 2, 2 and 3, right? Very first, what you have to do, you have to check the jumps, from what are the jumps are there, right? So for very first step, we'll find the possible jumps, and these are the possible jumps are there. Means from 0 we can do, from 1 we can do, but from 2 we cannot do, right? Understand? We can go from forward from 0, backward from 1, but from 2 that is not possible, no jumps possible. Okay, I hope you understand. Then in the next step we'll find the reachable max. So what are the reachable maxes there? Okay, let's try to understand. Okay, let's understand here. Okay, itself we're able to see. So what are the reachable maxes there? So from 0 you can stay at 2, we can say, or jump to 0 to 1 here, from here to here, right? We can jump. The maximum reachable is 2, we can say. From 1 we can go back to where, at 0, and it is reachable to reach to 2. So the maximum is, for this case is 2, and for this case is 2. Now from 3 we are stuck at 3, we cannot move anywhere, we cannot make any jump, and so it is, we can say we are at 3. So can we say that 2, 2 and 3 are the possible answers, right? I hope you understand. Let me try to okay, let's, if you have any doubt, let me know in the comment section. I'll go through the other examples. I'll try to put the example approaches there. Okay, let's try to understand the intuition. So let's understand intuition. So can I say, when we want to do jumps, right? So jumps as edges, What are the possible are there? We have forward jumps that we can do from I to j. Only if j is, we can say if j is greater than I, right? You can check the rules there, right? I've given you the example where nums at j should be less than nums at I. Very first, when we do the backward, right, that time if we'll go from I to j, your condition is if j is less than I and nums at j should be greater than nums at I. Can we say that? So when we will put these two together, right, so we can say, right, sorry, clean all, okay, fine. So when we merge them, or you can say put them together, so we can say for any I less than j, if nums at I is greater than nums at j, then there is a valid path between I to j. Valid path. Understand? Because from I we can go to the forward to j, since nums at j is less than nums at I. And when we want to go from j to I, that is called backward, right? Here the nums at I is greater than nums at, that is what we have. So the graph is undirected. Understand? Because one is going from I to j, another is going where? J to I, that is backward. So this is an undirected graph. Are you understanding? So that is why I'm saying we can say jump as edges. Okay. So if we will jump as edges, so this is possible because an edge between I and j exist, correct? Exactly when the nums at I greater than nums at j, right? Okay, so what do we need? So if we'll say for index I, right, the answer is the maximum value in its connected component, correct? Because we are seeing the undirected graph. So in any undirected graph, we can find the maximum value in the connected component, right? How? Let's understand how. Let's suppose we have an example. We can say 20, 21, 25 and 15. Can we take? So is 20 is greater than 15? This is ace. This is an ace. 21 is greater than 15. Ace. 25 is greater than 15. This is also ace. Can we say that? Right? So all these nodes are connected. Right? You can say all these nodes are connected. And so we can find the max. What is the max? Max is all can reach to the max is 25. This is a reachable max, right? So in the naive approach, what we can do, so the graph we can build, right? But that is become a too big, right? Because see, n we have given is what? 10 to the 5, if you see that, right? So we can check all the pairs I and j. To we will add the edges, and that will give you O of n square. And this is really impossible. Okay, so we cannot use this. So what is our observation? Think. So we don't need all the edges. Very first, we don't need all the edges because edges can be very, very big here. So if there is a path between two indices I and j, we can say we only need the enough edges to keep them in the same component. Know the component, right? Multiple components are there, right? So when we'll check, let me, okay. So let's understand through the example. Okay, if I'll say 2 is greater than 1 and greater than 0, so we don't need any is we can say 2 0 and 2 1 and 1 0. Understand? So if 2 is greater than 1 and greater than 0, so we don't need any ages like 2 0, 2 1 and 1 0 all together. So when we represent the connection is enough to put them in the same component. We'll just put them in the same component, right? So what you are understanding now? So this leads to a divide and conquer. Understand? Divide and conquer you can apply, or the monotonic stack. So these are the approaches can build a what? Minimal set of aces if you are understanding the algorithms, right? So this approach gives you the this problem, or you can say intuition, gives you two approaches. Either you go to the divide and conquer, and either you can go to monotonic stack. So these approaches will give you to build a minimal uh, set of aces, right? That preserves the connectivity, you can say, right? I hope you understand. If you any doubt, let me know in the comment section. I'll go through the example. I'll try to cover in the deep dive session. Okay. So very first, what we need to do. So very first, let's understand through the high level approach. Very first, we'll model the problem as a graph connectivity, where we'll take all the nodes equal to indices. So the A's between, you can say, I and j, if num set I is greater than num set j, right? And I is less than j. And then we'll try to find the connected component. Find the connected components. So all the indices in the same component will share the same answer. What is the answer? Maximum value of their component. And then in the third step, what we will do? We'll try to find the efficient A's construction, we can say, that will give you the O of n square. So we'll use the divide and conquer like a merge sort, right? And we'll split into L and M and R, right? Low to medium, medium to right. You can say left to medium and medium to right, right? And we'll connect left side node that are greater than the mean of the right side, and we'll connect the right side node that are smaller than the max of the left side. And we'll recurse this both half that will give you, or it will ensure that we need enough edges to connect the component correctly, right? So what we'll do, we'll try to our focus will be there. Take n log n, right, and solve it, right? So we'll use the DSU, disjoint sets union, right? And it will keep track of the connected component efficiently because we need that. And we'll, after building the connections, we'll compute the max value in the each component and we'll fill the answer for each index. Let's understand how. So can I say that, okay, if you see, if you understand the DSU, you need the parent, right, and the rank. Okay, if you are my student, you are already aware with that. Let's go with the solve. We'll get a solve. It will build the component that will do the complexity, present complexity. We'll build the, for each component, find the max value, right? To find the max value, we'll take a array component max, right? And we'll fill initially with the mean value and we'll try to find the max. Okay, and then each answer you will fill it and you will return the answer. But you have to approach the DSU, right? So you know that how your DSU works. You need the parent, rank, announce you will take, and this is your find method, this is your union method, right? These are the things we required. And so you know, this is the solve method where we try to connect all the component across L to R, right? And this is the way we will do. Okay, we'll find the left, the right, and once you have the mean L and max mean R, what you need to do? You need to connect all the elements that have the, take the union, right? You will do the union is greater than all the, if the elements are greater than, right? Then you'll try to connect all the elements that have the first left max. So you do the same for that, and you the union. Okay, like this we will connect all the component across the what do you call the components, right? So that's all I have in this video. Let me know the comment section, understood or not. I'll try to cover classes my student wants. That's all. Thank you guys. Thank you for watching this video.